All right, so our final talk before a 10-minute break is going to be Deborah Morales from the University of Las Vegas, Nevada, talking to us about ocean redox change across the early Mississippian. All right, so Deborah is here, and so I'm going to go ahead and ask you to start sharing your screen once you're ready.
Hello, everyone. My name is Debbie Morales. I am a PhD student working under Ganqing Jian at UNLV, and today I'm going to talk about redox change across the early Mississippian KO δ13C excursion. So the early Mississippian lasted from about 359 to 347 MA. And during this time, the Earth's surface environment were considered to have been oxygenated. However, the early Mississippian was also part of a critical transition from greenhouse conditions to the Late Paleozoic Ice Age. And it also shows the largest carbon isotope excursion of the Phanerozoic of up to 7 per mil. So the KO excursion, which is also known as TICE, is interpreted to have resulted from enhanced organic carbon production and burial. So organic carbon decomposition depletes oxygen in the water column, and then carbon that isn't decomposed is buried, causing fractionation of carbon-13 and carbon-12. Ocean anoxic events have been associated with δ13C excursions through Earth's history, such as the OAE2 and during the late Ordovician and in the Devonian. So previous work by Maharan et al. 2018 found up to a 6 per mil positive shift in carbon-associated stable sulfur isotopes, or δ34S, CAS. This positive shift in the sulfur isotopes suggests an unusually fast pyrite burial event at the peak of TICE. And a pyrite burial event could have been caused by expansion of ocean anoxia, but shifts in δ34S may have just recorded a local signal. So therefore, to understand the global redox conditions across the KO excursion, δ13C excursion, further redox studies are needed. So another study by Cheng et al. 2020 found evidence for the expansion of ocean anoxia across the first peak of the KO δ13C excursion using uranium isotopes. Uranium isotopes are interpreted to record global ocean redox signals. However, the uranium isotope anomaly seems to occur before the sulfur anomaly. So uranium isotope anomaly, and then it's occurring before the other proxies, sulfur here. So we use cerium or rare earth elements, particularly the cerium anomaly, to study even more ocean redox during this time. Cerium is redox sensitive, occurring in both 3+ and 4+ oxidation states relative to the other REEs, except europium and I think a couple others, but not redox sensitive. Anywho, the anoxic environment, Ce3+ is partially oxidized to insoluble Ce4+ on the surface of manganese oxides and hydroxides, and then it's removed from seawater, depleting the remaining seawater of cerium, and this is called a negative cerium anomaly. Below the manganese redox line, however, cerium can be redissolved back to the water column and enrich the water column again. So under anoxic environments, you'll have high cerium concentrations and no negative anomaly. In the modern ocean, cerium anomaly values are mostly below 0.55, but in the ancient ocean, increase of ocean anoxia may have led to higher values. And these values are recorded in well-preserved carbonates. The calculation for the serum anomaly used to compare it to lanthanum and praseodymium, its two neighbors, but seawater also has a positive lanthanum anomaly, which could exaggerate a potential serum anomaly. So an updated expression compares cerium to praseodymium and neodymium. When these values, these concentrations are normalized, they produce a seawater signature, which includes a negative serum anomaly here, an increase from light rare earth elements to the heavy rare earth elements, and a positive yttrium-holmium anomaly. So we sampled 2 Mississippian sections that show correlatable carbon isotopes here. One section is in Mountain Home, Utah, and the other section is in the Paranagate Range about 2 hours north of Las Vegas, near Alamo, Nevada. I will briefly talk about analytical methods. We cleaned hand samples with molecular water and then digested them in weak acid. We also use procedural and acid blanks and isobaric and drift corrections to account for any influence from the acid. And then some samples were repeated to ensure consistency. So in the PR section, a significant increase in the serum anomaly is associated with increases in the δ13C values. Here and here. And yttrium-holmium ratios and trace elements indicate that there was that the samples were of marine origin, so no substantial diatonic alteration or contamination from terrigenous material. There are 2 negative shifts of the serum anomaly here and here, and these are associated with occurring under major flooding surfaces in the section. Now in the Mountain Home section, we see similar features to the PR section. Again, the data were not significantly modified by diagenic processes or contamination, and high serum anomaly are associated with increased δ13C values. Then serum anomaly seawater values, or values that are closer to seawater, are associated with a flooding surface, major flooding surface, and an unconformity. Other way. Major flooding surface, an unconformity, and a major flooding surface, respectively. So in both sections, positive serum anomalies imply that there was expansion, ocean anoxic, expansion of ocean anoxia across the KO excursion. And the occurrence of the anomalies occurred in shallow water carbonates, including grainstones. So it suggests that the anoxia may have been widespread. However, the causal relationship of these anoxic events still needs further investigation. To summarize the redox studies used so far, we had sulfur, uranium, the serum anomaly. These all indicate expansion of ocean anoxia across the KO δ13C excursion. Uranium is considered a global proxy, but it happens first, followed by the serum anomaly and sulfur isotopes. And the duration of the serum anomaly seems to be much longer than the others. So we have to, there's still a question or potential to study this ocean anoxic event to find out what the causal relationship or this phenomenon was. So in conclusion, serum anomaly values show increase across the KO δ13C excursion. Petrographic analysis and major and trace elemental patterns indicate no substantial diagenetic alteration. Increases of the serum anomaly at the peak of δ13C in shallow water carbonates suggest that there was expansion of oceanoxia. And these redox proxies, including the serum anomaly, all suggest that there was oceanoxia across the KO δ13C excursion, but the timing seems to differ. So this relationship of local versus global anoxia across the excursion needs further investigation. Thank you.